All right, so we know that exponents and logarithms are inverses of each other. So when we're graphing logarithmic functions, we're going to start by graphing or figuring out at least the coordinates of an exponential function, and then if it's an inverse, you just flip the x and y coordinates. So that's how we're going to graph our logarithmic functions here. So we have f of x equals 3 to the x power. Eventually the inverse of that, oh gosh, will be f inverse of x equals, and then the logarithmic version of this, we would write that as log sub 3 x. This is what just the equation would be. Not a huge deal. So let me grab a calculator because that'll make this so much faster. Now it's telling us what to put in for x. It tells us to put in -2, -1, 0, 1, 2. Now 3 to the negative second power would be 1 over 3 to the second power, or 1 over 9. And decimal form of that would be 0.1 repeating. Let's just call it 0.1. If we were to put in -1, 3 to the negative first power would be 1 over 3, which is 1/3, or 0.3 repeating. Again, you could leave them as fractions. We're just going to do decimals, and we're just kind of getting a general graph of it. We're not doing a perfect 0.3 repeating. We're not going to be able to tell the difference between that and 0.3 on our graph. If we put in 0 for x, in the original function, 3 to the 0 power is just 1. If we put in 1 for x, 3 to the first power is 3. And if we put in 2 for x, 3 to the second power is 9. So we're just going to scale our graph to make sure we include all of that. Our highest number we have is 9. So we have to make sure that we include at least 9, and we should probably do that same scale in every direction. So let's just make it 10 like we usually have on the graph. So we'll make this 10, half of 10 is 5. So we'll have that going kind of in every direction, a 5 and a 10. And we could have -5, -10 too. Now I was going to put pre-made graphs on here, but I wanted to allow for scaling for us in case we have some very large numbers as well. So let's graph these points. -2 and 0.1 is like here-ish, right? That's going to be way down there. We have -1 and 0.3 would be a little higher. We have 0, 1 would be about there. 1, 3 is about there. And then 2, 9 would be about there. So exponential functions, woo! They approach the x-axis. Now, if that was a perfectly drawn graph by a computer, it would never actually technically touch that x-axis, but I know this might be hard to believe. I'm not perfect. So that's what we get. Now the inverse of this, the logarithm sub 3 of x. It would be reflected across the diagonal line of y equals x, right? All inverses are. But really, we'll see that if we just flip the coordinates. So the inverse coordinates would be 0.1, -2, 0.3, -1, 1, 0, 3, 1, and 9, 2. So we're going to graph these coordinates when that eventually shows up. Oh boy. Got a little sloppy there. All right, so 0.1, -2, something like here. 0.3, -1 might be here. We're at 1, 0, 3, 1, probably about there, and then 9, 2, something like this. Now, if we were to tie in domain and range here, the domain of the original one, it would never hit 0, but also like left and right domain, there'd be no limit. So the domain on the original would be all real numbers. And remember, when you're graphing inverse graphs, the domain of one would become the range of the other. So the range of our inverse graph would be the all real numbers. Now if we're looking at the domain of the original graph, the range is up and down. Technically it would never hit 0. So if we were listing the range on that, usually if it hits a number, then we would put a bracket on it. But since it will technically never hit 0, we could put a parentheses on that, and then it goes towards positive infinity. This would become the domain of our inverse function. 0 to infinity. We are going to do that same procedure 3 more times for these graphs. Substitute in the numbers for x, solve them, and then use the inverse coordinates. That's it. All right, now it's telling us we're going to plug in -3, 0, 1, 4, and 7 for x here. -3, oh, come on, there we go. 0, 1, 4, and 7. These were the x coordinates that they gave us, which, if we're flipping these, those will eventually be the y coordinates of the inverse. Now we need to figure out the missing part. So let's substitute these in here. 0.8 to the -3rd power. 0.8 -3rd, 1.95. All right, 1.95. So that will become our other x, 1.95. 0.8 to the 0 power. Anything to the 0 power is 1. 0.8 to the 1st power is just going to be 0.8. 0.8 to the 4th power, don't know. 0.4096, so let's call it 0.41. And then 0.8 to the 7th is 0.2097, so we'll call it 0.21. So we have all of our coordinates. Here's our exponential graph, and then the inverse would be the logarithmic graph. So we could write that equation as f inverse of x equals log sub 0.8 of x. All right, great. We have to make sure all these coordinates are included. The highest number I see there is 7. So we have to make sure that at least on every axis we go to 7. I'm going to make it 8 because 8 is pretty easy to kind of divide from there. 8, 8, -8, -8. Because half of 8 is 4. So this will give us a nice easy marking for that. And then we can cut those in half, and we don't even need to label them, but then it's like we're going by 2s. And sure, in theory, if you wanted, you could even cut those in half. But I think our eyeballs can do that as well. All right, the first one, we have -3 and 1.95. Here's -3, here's about 1.95. We have 0, 1. We have 1 and 0.8. There-ish. 4.41, that's about half of that, and 7.21, that's half of that. So, if this was drawn correctly, I mean, we know it's exponential decay, so it would start high and it would start dipping low. So it would start, you know, as it went further and further left, it would start getting a little steeper. But that would be our graph. Now domain, left and right, there is no limit. So our domain will be all real numbers here. And remember, that becomes the range of our inverse. that'll show up in a moment here. Maybe not. Oh, there we go, and it changed colors on us. Nice. Now, the range here, again, it approaches 0, but it never hits 0. So our range is going to be 0 to positive infinity, which means our new domain of our inverse would be that same thing, 0 to infinity. All right, now we're going to graph the inverse. We'll graph it in blue. So 1.95, negative 3, about there. We have 1, 0. We have 0.8 and 1. 0.8, 1. We have 0.41 and 4. We have 0.21 and 7. So there's our graph. Remember, they should be reflected over the line y equals x, which is just a diagonal line through the coordinate plane, which those are reflected. As poopy as my graphs look, as terrible as I am at drawing them, they are reflected over that line. Now we have 2 more, and it says you try these, so we'll go a little bit quicker through these ones, but feel free to pause and actually give them a try yourself. All right, 5 to the x power. 5 to the negative second would be 1 over 5 squared, 1 over 25, which is 0.04. 5 to the negative first would be 1 over 5, which is 0.2. 5 to the 0 power is 1. 5 to the first power is 5. And 5 to the 1.5 power, I don't know that. 5 to the 1.5. 11.18, we'll call it 11.2. So we're going to get the inverse of these. And we could write the equation log, so 5 of x equals f inverse of x. I probably should have wrote the f inverse of x first, but it makes no difference. So we'll have 0.04, negative 2, 0.2, negative 1, 1, 0, 5, 1, and 11.2, 1.5. So I got to make sure I include 11.2. I'm just going to bump it up to 12, because again, 12 is kind of easy to split. Half of 12 is 6, and then we can make it 3 and 9, but we don't need to label. So 12, 6, 3, 9. Negative 12, negative 6, negative 3, negative 9, negative 12, negative 6, negative 3, negative 9. All right, first graph, we have negative 2, there-ish, 0.04, pretty much on 0. We have negative 1 and 0.2, a little bit higher. We're at 0, 1, that's about there. 1, 5 would be up here-ish, and then 1.5, 11.2 might be up there. So, domain, all real numbers. Our range, again, it's always going to be above 0. So our range, we could say 0 to infinity. Those are just going to flip on our inverse here, so I'll go ahead and do that now. The inverse domain would be the 0 to infinity. The range would be all real numbers. And then we just need to graph the new coordinates. 0.04, negative 2, up there. We got 0.2, negative 1, there-ish. We got 1, 0, 5, 1, and 11.2, 1.5. Are those reflected over the line? Y equals x? Yeah, all right. One more. All right, 0.5 to the x. Now that's exponential decay, so it'll dip. So 0.5 to the negative. You know what? I'm going to do this all in red. And I'll do it all in green. Alright, 0.5 to the negative second power is 4. Oh, that's fun. 0.5 to the negative first power, it's going to be 2. Alright, anything to the 0 power is 1. Look, they're dividing by 2 each time. So 1 divided by 2 is 0.5. 0.5 divided by 2 is 0.25. Alright, you know what? Let's graph that first. Our highest number is 4 there. So we're just going to make sure we include at least 4 in every direction. 1, 2, 3, 4. 4. After that is 2, 3, 4, negative 2, negative 1, negative 3, negative 4, negative 2, negative 1, negative 3. Alright, so we'll graph this one in green. Negative 2, 4, negative 1, 2, 0, 1, 1, 1 and 0.5, and then 2 and 0.25. There's our exponential decay. Domain, all real numbers, no limit right and left. Range, it's all at least 0. Great. All right, the inverse. We'll have f inverse of x equals log sub 0.5 x. Flip the coordinates. 4, negative 2, 2, negative 1, 1, 0, 0.5, 1, and 0.252. The domain and range flip from the original function, so our domain would be the other range, 0 to positive infinity, or you could say x is greater than 0 if you want to list it that way, and then the range will now be all real numbers. All right, 4, negative 2, 4, negative 2, 2, negative 1, 1, 0, 0.51, and 0.252. Double check in your brain. Do these look like they were reflected over a diagonal line here? Y equals x. Yeah, they do. And my graphs aren't even that spectacular. That's it, man. That's all we got to do today.